Recording. That turns out. So I'd like to introduce our speaker, and John Carney. He's a CID application engineer architect from Cadence. He graduated from Southern Illinois University with a degree in electrical engineering. He immediately got recruited by OrCAD for technical support and became part of Cadence in the 2000 acquisition. He became a SoCal field application engineer in 2005. Currently serves the San Diego IPC Designers Council Chapter as the education chair. And has a passion for engaging with customers to make them more efficient with Cadence Lego software. He supports the entire Lego product line, schematic entry, PCB layout, package layout, PSPI simulation, signal integrity. He's going to talk to us today about that. John, we got to do a little
right into it. Thanks everybody for coming. I appreciate you seeing my name and my agenda and still deciding to come anyway. You know, early in January, I think late December, Scott called Cadence and said, hey, I've got an IPC meeting coming up in January. Send us your best speaker and your best topic. That guy was in Florida, so you got me instead. So hopefully you learned something. We're going to start out by covering Maxwell's equations. No, I'm just kidding. This is really just out of respect for the guy. The fact that this guy, back in the day before there was computers, was able to figure out electromagnetic waves and their interactions with everything, which is phenomenal. So I always pay credit to that guy. But the key thing that you're going to want to keep in mind, especially later on, I'm sure all of you have seen this in one way, shape, or form, is the fact that the conductors on your PCB, it's not just little ones and zeros floating all over the place. Everything's an electromagnetic wave. Every pulse of energy is an electromagnetic wave that couples and propagates all over the place. And really what you're trying to do as a PCB designer is trying to control that as much as possible to get the desired effect at the receiving devices, right? You want it to measure a 1 or a 0, but in reality, it's just electromagnetic waves. I'm sure every presentation that you go to talking about high speed has an introductory slide, almost exactly like this. This is my version, right? Why do you have to care about high speed? Because things are getting faster. As things are getting faster, you know, what qualifies as high speed is really open to debate. It's really at whatever speed and whatever size of structure you're dealing with that speed could become a problem. One of the biggest issues is not just the speed at which the clock is pulsing, but the edge rate, the transition from the 0 to the 1. Like a huge induction of voltage into a line that was otherwise idle is a huge burst of energy. If that happens at a slow transition rate, that's one thing, but it's happening very rapidly, that's another level of problem. And DDR4 SerDes are now going up into the 5 gig, 12 gigahertz range, so these problems aren't going away, they're becoming more and more predominant. So, first thing I'm going to talk about is back drilling. Probably a lot of you have already heard of this, probably a lot of you do it, but the reason you want to consider about back drilling is if you have a through-hole via going from the top of the board all the way to the bottom, multi-layer board, 4-layer, 6-layer, 8-layer, this gets worse the more layers you have in your design. And if that's a through-hole via, and if you only route that signal out on the second layer from the top and you go all the way across your board and then back on the top, what happens with the energy of that signal when you shoot that into that via? Most of the energy goes through the via and out the trace where you want it to go. Some of it also goes all the way down to the bottom of that via stub, can't go anywhere else, bounces back up, and is like a secondary signal going down that line. Okay? Conceptually, it's the same. Like no PCB designer, if you routed a trace like this and then just routed something like that, that would not be good. Everybody knows not to do that. A via stub is pretty well the same thing, just rotated 90 degrees in space.
Excuse me.
Yes.
My question is I've been trying to find this out. Is what instead of back drilling, you know, a micro via would do the same thing. Which is more cost effective and which is actually better?
There's so many trade-offs in that question. What you do, I think, from a performance perspective, a micro via is going to kind of accomplish the same thing as back drilling out a through-hole via. What's more cost effective on your design? So many things to consider, right? How much volume are you doing? Are you going to be back drilling out? Do you have a design that has only 10% of it are high-speed signals that would need to be back-drilled, or is it 80% signals that need to be back-drilled? And some tools give you an option to look at the design and figure out how much back-drilling do you really need to do to have an effect on the signal integrity, right?
Yeah, but if you're already using micrometers, why would you backtrack?
Right, if you're already using microvias, probably not, right? There may be other manufacturing considerations that would come into play, but yeah, if you can get away with a microvia, then back-drilling is not going to really buy anything. So you're effectively doing the same
And
thing.
if your signal has to go down deeper layers, that's why we can't.
Well, that would be a different thing.
Right, yeah, if you can just get two from the exact same layers, yeah, you're doing the same thing. So if you were to consider in time, right, putting away the idea of it all being a bunch of EM waves for a second, if you just had a transition of what you wanted the original signal to be, going from a high to a low state, right? A few nanoseconds later, you're going to get some noise and some distortion on that signal from that extra energy being bounced back from that via stub and coming down the line. Whether or not that's going to be a problem that has to be dealt with, there's a lot of things to consider in that. Maybe the length of the trace is such a way that those reflexive signals are going to compound themselves on top of the original signal and they're going to amplify and distort that original signal. Maybe the transition line is at such a length that the frequency of those distortions are going to be gone before the receiver even sees them, right? So it's not a thing of you just always have to back drill. There's some other things that come into play, but that's effectively what happens when you look at it. And I'm going to start showing you all these effects of issues in a single transition from 0 to 1, so that we start kind of talking about eye diagrams, which is really the effect of, if you think about every time you are listening to a song on YouTube or take a picture and send it to somebody, or you pull up a web page on Amazon, right? The collective amount of ones and zeros that had to be moved to present that data to you is in the millions and billions, and it happens all the time. So getting every single 1 to 0 transition clean and perfectly on your system is important. And so drilling away the via stub, right, that can eliminate those reflection issues. But like you kind of asked, do you need to back drill all of them? No. It's always going to be a trade-off of cost and performance, yeah.
It's not like, instead of just going down layer 2, you go down to like the bottom -1 or something, or -3. Do you still need it, or when do you really?
Yeah, so that's when you almost have to start measuring the signal and seeing what the effect of a 6-layer via stub is going to be versus a 1-layer via stub. And the effect of that is probably going to be, if you imagine, this is kind of at a very high abstract level, is how long after the desired signal does that reflection noise come on top of your signal, right? The smaller stub is probably going to happen a lot faster than the larger stub. And so you don't necessarily need to back drill your V in your design. It's a factor of how quickly are those things switching. Is that noise going to compound itself to affect what the receiver ultimately needs to interpret as a 1 or a 0, right? And there's most software out there that has back drilling abilities in there, has an ability to say, what happens if I back drill everything? How many back drill hits do I have on my board? What if instead of back drilling everything, I just got rid of every stub that was greater than this distance, right? Your SI guy might come in and say, you know what? Even though you got a 10-layer board, I just don't want to see a stub greater than 2 layers. Maybe let's just back drill all that stuff, so you may have some stubs, but none that are at a distance enough that's going to cause a problem. You wouldn't just want to just blindly back drill and just assume it's going to make everything better, because then you spent money on something that maybe you didn't have to. And I'm also going to be clocking through these presentations kind of quickly because we don't have a ton of time for it. So the second thing to think about is impedance, right? You got a driver, you got a receiver. Those things have some sort of characteristic impedance with them already. You want to try to have the transmission line match the impedance, so there's not an impedance discontinuity, because impedance discontinuities can also cause reflections in the signal or the energy that you're trying to propagate from the driver to the receiver. It basically looks at an impedance discontinuity as if it's like some resistor or some little wall that it has to get through, that also makes the receiver not see the desired effect of what the sending device sent out. And so if you have, looking at the same thing of an ideal perfect waveform, when you have everything that's matched impedance, there's not a lot of distortion on the receiving waveform. But if you have an impedance mismatch or an impedance discontinuity, you're going to have overshoot and undershoot measured at the receiving device. So it's kind of the same thing as having a back drill issue. It's just another cause of extra glitches in what you would like to have a perfect 1 and 0. And so when you get a big design, right, you already have thousands of things in your mind to keep track as a PCB designer, so you try to work with your fabricator and say, here's my stack up, tell me what I should route my traces with to achieve the desired impedance, right? You're not just going to go in and just think, I'm going to route everything 8 mils wide or 6 mils wide because that's how it fits. You already at the start of your design probably have some sort of guidelines, or you use an impedance calculator with your stack up, or got some recommendation from your vendor to say these are what these transmission lines need to be routed at. But still, when you get done with your design, how do you know, did I violate an impedance problem anywhere in the design? And so I would recommend taking, there's tools all over the market that can analyze things like this for you, that you may have a design where you know everything was great, and then all of a sudden the fabricator comes back and says, hey, your dielectrics are a little bit changed, or swap these layers in your stack up for some reason, or get rid of these layers, or add an extra ground plane layer. You may want to quickly know, everything was perfect before in my impedance world, how badly did that break it, right? Do I have a whole bunch of nets now that the impedances are completely violated? Or you might have rated everything perfectly, but you may have had like 1 or 2 cases in the design where you had to trim down a segment just to get it in there, and now you have a small segment of etch that has a different impedance than the rest of it. Is that going to cause a problem? Maybe it will, maybe it won't, because there's kind of 2 ways to look at the impedance of a line. There's what would be called the characteristic impedance, meaning you have a line that goes all over the place. Maybe it goes over voids in the plane layer, maybe it changes widths. It's changing impedance as it's going along there, but collectively you could say it's still a 50 ohm line, more or less. Some places it gets a little higher, some places it gets a little lower. So maybe dropping down to like 45 for a short segment, maybe it will cause a problem, maybe it won't. But at least then you can look at it and say, hey, as a designer, maybe I can increase that a little bit and get rid of that problem. Or there's something like this where you see, there's a large gap of impedance discontinuities there. That's clearly because there's 2 different reference planes going on there. As a PCB designer, are you going to fix that by changing the width of those lines just in that point? No, you're not. Then you have to figure out a different routing strategy, find out how important it is for these things to have a good reference plane or something like that, right? Maybe at one point in time they did have a solid reference plane, something changed, and then now you realize, oh, now I might have an impedance problem. So how do these kind of things, all these little minor effects, affect what you're really trying to accomplish with your circuit, right? Most of the time when people think of high speed, they're either dealing with a SerDes interface or a memory interface. And so you got to move on from thinking about a single transition from a 0 to a 1 or a 1 to a 0 to millions or billions of them, right? You're cramming down, like I said, when you're downloading that song on YouTube or watching that streaming video and stuff like that, just imagine all the billions of 1s and 0s that have to be coming through all your systems, all the memory on your computer, all the memory on your phone, coming from wherever, going through all the data centers. And so what happens to all this data, or the way people like to measure that data, is they use a thing called an eye diagram, right? Imagine if you were, looking at a board that had a DDR4 memory interface, and you're like, I want to make sure this thing works. And at one point in time, they handed that to some SI person and said, all right, measure every single 1 and 0 and make sure they're all a 1 and 0 at the right time. And that SI guy said, heck no, I'm not doing that a million times. So they came up with this idea of an eye diagram. And so if you were to think of a stream of 1s and 0s, right? This is just say 1 bit 0, or lane 0, right? 1s and 0s, 1s and 0s, and you got a million of them. So what you do is you kind of take this waveform and you start folding it on top of each other. Every time step, you just take that waveform and superimpose it on top of each other over and over and over and over and over again. And what that ends up looking like is an eye, right? So this is a transition from 0 to 1 to 0. Here's another one, here's another one. If you were to zoom into that, you could see, thousands of different waveforms in there. And what effectively they're trying to do is look at right here in the middle of the eye, this is when your DQ signal's going, or this is when the clock signal's hitting. This is when that receiving device is actually looking at that signal to determine, did I get a 1 or did I get a 0? And so the idea of an eye diagram is make that eye as big as possible so when the receiving device gets it, it's clearly a 1 or a 0. So those effects of the impedance issues and the issues of the back drill can cause these eyes to close, because you can think of every little distortion that's up here at the high level or at the low level, any sort of shift in the time will cause this eye to close a little bit. So that's why all these little things that you're doing by back drilling and fixing impedance and minimizing crosstalk and coupling they ultimately all add up to a good eye diagram. That's what your final SI person is really caring about, right? Because you're not just fixing one transition from 0 to 1. That's not a big deal, but you got to get every single one of them right. And so another way to think about what an eye diagram is, if you were to think just these 4 bits, right, going 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0. If you were to overlap those things, you end up with something like this, and this is what they call the resulting eye. And so this is just looking at it another way, is taking this huge stream of just constant switching ones and zeros, you overlay them on top of each other, you end up getting this squiggly eye diagram where they end up looking at it something like you can look at it in the contour. If you ever see this contour type of display, you can kind of think of it as the height of those bumps is how many waveforms are hitting at that point versus a low point, there's not that many. And so then what vendors are ultimately going to give you is what they call an eye mask, is something like this, where it's just take all that eye information, just give me the innermost contour of that eye, and then like a memory interface vendor is going to say, this is the mask. As long as you can fit this shape inside that eye, you're good to go. So that's really what's going on. So like I said, when you take a picture of your dog and send it to somebody, you're like, hey, check this out. That picture gets distilled down to a whole bunch of ones and zeros, goes from your phone to the memory on your phone to an antenna to a receiver, all over the place, and then gets reconstructed as a picture of a dog on the other end. And if the eye diagram's not right, the dog doesn't look so good. So things that can also affect that eye, right? So if you've ever run a memory interface, you're going to have all these nets, and you have to deal with propagation delay or relative propagation delay. You got to make sure they all get to the receiving device at the same time. The reason that needs to happen is shown here is all these things are not the exact same length. So what that'll do is it'll make half the transitions from 0 to 1 up here, and the other half will be way over here. So some of them are getting there, yay, that's a 1. A couple nanoseconds later, oh, here's the other one. And so that can cause that width of that eye to kind of shrink, almost to the point that it's closed, because if all the zeros and ones that make up the whole set of data are getting there at separate times, then some are here, some are way over here, some are coming up over here, so that eye starts to shrink. And so that's why when you match those things, get them all the same length, you can kind of conceivably think that that's making the width of your eye the most possible it can be. And then everybody also, you probably also got somebody screaming at you, well, make sure the DC, make sure it has enough power going to the device. You can kind of conceptually think about that as getting the eye height taken care of. Because if you've got a device that's, its active high state is like a 1.2 volt device, right? You got a 1.2 volt power rail, you're routing it to that device. When that thing's supposed to be a 1, it needs to be able to go all the way up to 1.2 volts. If it can't, because it doesn't have enough copper going to that device, then instead of going all the way up to 1.2 volts when it's high, it may go up to like 1 volt or 1.9. Or if the ground's messed up or the ground's noisy, it may not be able to swing all the way down, so you can kind of think of it would shrink that eye a little bit. So you can have compound problems of data coming early, data coming late, impedance and reflection, shrinking that eye this way, bad voltage and noise, shrinking that eye that way. So all these little things that your SI people are constantly asking you to take care of and deal with, this is their ultimate goal of what they're trying to accomplish more or less. So, kind of throw out some other cool keywords out there. Someday some of you may hear somebody saying, oh, we're doing PAM3 or PAM4. So, 0 and 1, that wasn't good enough for people. People needed to cram even more data down some of these high-speed SerDes lines. So, what this basically stands for is pulse amplitude modulation. And the idea with that is instead of a single 0 or 1, you now have 3 logic levels. 1, 2, 3, or 4. 1, 2, 3, 4. So this is popular in the automotive industry because they're having to, transfer a ton of data from different portions of processors in the vehicle and out of the vehicle to wherever else it needs to go, and just single ones and zeros wasn't cutting it. A lot of it also because automotives are super, super noisy, and they're using the cheapest twisted pair cable all over the place. A lot of it they're doing it just for redundancy. Let's send the same data twice and then compare it at the end to make sure everything's in place. What's that?
So it's not using the 0 and the 1, it's using...
Yeah, so you kind of got 4 different logic states: 0, 0, 0, 1, 1, 0, 1, 1. And so you can kind of think of it, you're shoving twice the amount of data down as what you had before. But it's also, imagine what you had to do to get this eye diagram clean. The signals have to be super pristine to clearly measure this versus that. Because if these two in the middle are kind of crossed over, then you've kind of lost the whole point of doing all of it. All right. So switching gears a little bit, kind of more switching towards power, is loop inductance, also known as worthless decoupling capacitors. So if you were to do everything right with your design and get all your nets routed the exact same length and you got to get your eye diagram, everything would look good if you had that ideal power. So if this device is supposed to be operating at 1.5 volts, that eye diagram is going to look super cool. But then if you start taking into account coupling between signals, that eye diagram could look a little bit messier. But then if you come to reality with the fact that that power and ground plane is not always going to be completely solid 1.5 volts. Like if you imagine, a large IC or a memory device, and all of a sudden it's just rapidly switching on, off, on, off, on, off. The power underneath that device is going to be fluctuating a little bit. Above 1.5 volts as the device tries to switch on, it's going to draw a bunch of current. The power level is going to go down. When it turns on, it's going to bounce it back up. And so those fluctuations in power also mess with the eye diagram. You can see this clean power supply, wide open eye, noisy power supply. The eye starts to close. And so that's why you always have all these decoupling capacitors all over your board. The idea of the decoupling capacitor is to recognize that drop in that power next to the IC, because the decoupling capacitor is basically storing charge, right? When the device powers on, the power goes through the coupler, it fills up on charge, then it kind of acts like it's not there. But as soon as the capacitor senses that the voltage on its output is not the same anymore, it starts releasing all its charged energy. And so designers use that to their advantage by basically putting those decoupling capacitors close to the power supplies of the ICs, so when that power level drops on the IC, the capacitor says, oh cool, I've got some energy, boop, here you go, have it. Okay? So that's why you have all these capacitors connected to power and ground. And if you ever start to looking at a design, a hardware designer, you would never, ever, hardly ever see, I'm sure somebody, don't ever say never as an engineer, but you would never see them put a bunch of decoupling capacitors and then throw an inductor between the capacitors and the device that you're trying to recharge. Because the inductor is pretty well going to cancel out the effect of that capacitor in the first place. It releases the energy, and the inductor just uses it all up, and it never gets to the device. So, as a layout designer, your job, when the hardware designer says, cool, place all these capacitors as close to this device as possible, is to not accidentally turn them into an inductor. And so you basically want to do this. You want to eliminate something called loop inductance, because an inductor is basically just a coil of conductor in a wire, right? And so you can think of, you got your capacitor, but you got one end going to a power and another end going to a ground. You just made a tiny little conductive loop, so you want to make that loop as small as possible. If you put the cap on one side of your board and you mount it to the power and ground all the way on the other side of the board, or 20 layers in, you now have a large loop of inductance that this capacitor has to deal with before it can get its energy to that device. So you always want to try to eliminate doing that. Looked at another way, if you look at a design, you may have a design, every design I see has at least 500 of them, right? So I would always recommend, if you have the opportunity, analyze your design afterwards and see if you can have it tell you, where do you have capacitors that have high loop inductance based upon the way they're connected to many, many layers down versus the nearest power and ground plane layer. Another thing you have to contend with is placing those capacitors as close to the device as possible, because different capacitors can react to changes in voltages that's happening at a different speed or a different frequency, right? If the change is happening so fast, the capacitor can release its energy, but it won't get there in time for the device to operate on it. That's why a lot of times it's higher speed devices. You're seeing this is inside a VGA package, so this is what you see on the PCB. This is inside the package, and you're going to start to see capacitors. In fact, this has been happening for quite a number of years now. Capacitors inside the package. So these are decoupling capacitors for that IC. These are decoupling capacitors for that IC, because they just have to get that close. Otherwise, there's no way that they can effectively release their charge to get there in time to affect the switching of that. But anything that's been put on your board, most likely the hardware designer has realized that they can still have value on the board. And so generally you have to figure out, you have to trade with how close can I get it to the top side of the board, or can I put it on the bottom side of the board and still connect it without making that loop inductance problem. So you got all sorts of trade-offs to consider there. Return path vias. So earlier on when I showed that slide that showed the traces going over the void in the ground plane, I think everybody PCB designer knows to do that, right? You don't like route over a ground plane, then have a huge split, and then come back over to a ground plane. But when you're going from one layer to another layer, that's also all of a sudden a trace has a bunch of reference grounds, and then all of a sudden beside the via, there's no referenced ground. It's all of a sudden going from top layer to middle layer, something, something, something. So return path vias are starting to become a thing, right? Signal's always going to go back to its source, and so you can look at return path in a bunch of different ways. Is it going from one reference plane to another reference plane? You can look at the return path. Is it following the signal or is it not? Or do you have an impedance problem because of a return path problem? And so, yeah.
Good question. You have a ground level until you route down from 1 to 3. Do you need a via or
Only if you change your reference plane.
it'd just be going to the other side, right?
Right, yeah. And it also could depend on like how, I mean, if it's just going from layer 1 to 3, depending on how big that stack up is, because there is going to be a period where it's on 1, it's referencing the ground plane, then it's going through, and then it has the dielectric, and then the signal layer, and then the ground plane below. So it may be something you have to run an analysis on it to find out what's the effect of having this return path via, what's the effect of not having it, maybe the effect of how fast the signal's going, right? And so this is where you really have to start thinking of what's the electromagnetic field doing, right? What does the EM field really want to do when you're transitioning to these designs? And that's really what you're trying to control to your advantage, right? Because really, I mean, it's an electromagnetic wave that's transferring through the design. And so they exist between any two conductors, right? And so current always wants to flow in a loop. It's going to find a way back. Your job as a designer is to try to keep that way back as close to the conductor as possible. Okay. And so a lot of memory interfaces are even recommending, right, use a return path via and even use this particular type of return path via. So you got your differential signals, you got your differential via, put return path vias this close to those signals anytime you make a layer transition. And so you can even, if you run some sort of analysis, you know, high-speed signals, you can see that if you have a return path via, that the blue one is the one without the via, the one with the via, losing a lot more energy. This is basically what this is representing here to the conductors and the dielectrics around. It's just kind of losing energy, whereas when you have the return path via, it keeps it. And so the general guide, right, there's no one hard and fast rule of how you want to put these return path vias in, but you want to use closely impedance matched vias. Match your vias, same to signal vias. Put them in as close proximity to the signal vias, and also use a large clearance hole to clear that around from anything else around there that you don't want it to couple to. And also, people start to realize that even if you do something like this, that you put two vias in just for a differential pair, you kind of want to try to even eliminate these little bumps, this kind of snowman shape, and just have a nice solid peel-shaped void around those vias. Because just that little bit of additional conductor going in there causes enough coupling between those vias with the energy in the field around it, so half the energy that you want to get to your receiver isn't getting there. And so what a lot of tools now support is this ability of a high-speed via structure, right? So as a designer, right, if you have to route 20 differential pairs in your design, you don't want to have to draw that over and over and over again, so you can implement it once and then reuse it just like a library part. So every time you plunk in your differential pair vias, you get the whole shoot and match of whatever your SI person is happy with. And what we're seeing a lot of is it being a real simulation-driven type of via structure, right? Putting a ground via in is probably a good rule of thumb. Making it as close as possible, probably a good rule of thumb. But if you're lucky enough to afford people in your organization with SI expertise, more than likely they're going to take your stack up and they're going to take that differential pair signal and they're going to analyze the heck out of just a particular area, and they're going to dial in exactly what the spacing and stuff needs to be, and then they're going to give you that and say use this and only this and nothing else. And that's kind of ensuring that what's ever going on in that differential pair is going to hit the receiver correctly. Fiber weave. How many people have had to deal with fiber weave yet? One. All right, so fiber weave at high speeds, right? The dielectric, if you put it under magnifying glass, is not uniform. So if you have one trace going over one piece of the fiber and another one that goes over the place that has a lot of weave in it, it's an impedance mismatch. So how fast of a signal do you have to have where that's going to cause a problem? How long does it have to be where you have to have a problem? More than likely you're going to get some design guides, but what I believe it was Intel, the first people that asked us this like 10 years ago, they kept saying we want to rotate pieces of our artwork 10 degrees, and we finally figured out they were trying to do this. And so the idea is if you have to route a high-speed signal over a large distance, you can route it with these kind of jiggity-jog angles like this to eliminate that fiber weave effect, because now instead of having one signal over one reference impedance and another one over a different one, you get a uniform impedance of those two different signals. And we normally see these things at about 5 gig, right? And so you can even see measured amplitude differences of a homogeneous or with the fiber weave between two different designs. And to you that may not be a big deal, but that particular difference, like I said, compounded over billions and billions and billions of bits could affect the performance of your device. And do people actually use it? Yeah, they do. So this is an example of an open source design. And between these two processes, if you were to zoom into that particular area, you start seeing stuff like that. And then you even have to tune at the off angles and stuff like that. So if anybody ever says, I got to deal with fiber weave, you should be able to implement that in your tool. And this is the effect of running an eye diagram of the skew of the differential pairs. So like how quickly the skew is basically the measured effect of how quickly the signal gets from one side of the diff pair versus the other side of the diff pair to the receiver. So if you had a homogeneous dielectric, about 0.38 picoseconds. With the fiber weave, if you have a bad case where one side of the diff pair is on totally over the fiber, the other one's over all the holes, it goes up to almost 14 picoseconds. Tabbed routing, another interesting structure. How many people have had to deal with this? Okay, yeah, so yeah, this processor company came out with this idea. And the idea is to take your traces and to put all these little conductive tabs on it that can deal with far field crosstalk and also helps control the impedance. And so you would probably never just randomly throw these things on, because you definitely would not get the desired effect by just putting them on thinking, hey, this might help. You probably wouldn't have the space to do it anyway. But what you would get is if you're implementing a processor from a company that requires these things, is in their design guidelines, they would say, hey, for these signals, put these tabs on. And every PCB tool I've seen that implements this will basically give you a form, and you basically take the data sheet and say, yep, put these number of tabs, make them this high, make them this far apart, and then you just select your signals and it throws the tabs on there. And you can see what that does with far and crosstalk and your eye height and your eye width, with and without the tabs. Without the tabs, pretty shrunk. A lot of crosstalk problems. And you don't really even have to put them everywhere. So if you just route two parallel traces all over the place that's 8 inches long, this is a test case, not a real design. So just put them in just a small segment. It eliminates a lot of the crosstalk issues. So that's that same design with the tab routing example zoomed in close to the BGA. You can just need to smack those things in there. The last one, before I talk about you don't want to add inductance, we've had people come to us saying we want to compensate capacitance in the line by adding an inductance right at the pin of the BGA. So they requested an ability to add a small coil around the pin of the component right at the last minute to create an inductive structure at the end. All right?
What's the purpose of that?
The purpose of this is if you have, let's say, a line that has way too much capacitance, you can add this at the end, and it's kind of like dropping an inductor in the schematic. You know what? The people that asked for this don't want me to say who asked for it, but I thought it was kind of cool, so I added it. All right. So that was the first presentation. While I switch, let's take a quick bio break.
Question before.
Yeah, ask a question.